Okay, hello everyone. This video is for the introduction of the statically indeterminate axial loading. Okay, I demonstrate a very simple example for the statically indeterminate in axial loading. Okay, suppose we have a bar. We have a bar and claim in the two wall. A bar claim in the two wall. Okay. Okay, and the wall and these two terminal point I call it A and B. Okay. And then I apply the external loading 500 Newton and acting on the point C, and it's point down, and it's the external loading is point downward. And I'm asking finding the reaction force at the terminal A and terminal B. Okay, so that's it. That's just very simple, very simple statically indeterminate problem in axial load member. Okay, so why it's called statically indeterminate? That means okay, and in such problem, after you use the rigid body equilibrium, you will find you don't have enough equations to solve all the unknowns. And then you need to find another equation to solve the problem, and the name, and we will give the equation of names is so-called compatibility equation. Okay, and to me, this compatibility equation is, to me, is like a constraint. Okay, find a constraint. Okay, mathematically, I would say it's constrained. Okay, but in most of the mechanics of material textbook, they call it compatibility equation or compatibility condition. But to me, it's just the constraint. Find the constraint of the system. Okay, constraint is mathematically is called constraint. Okay, so so let's look at this. Okay, here this is the textbook. The textbook that draw the free body diagram of this bar, but I would like to draw a free body diagram by myself. Okay, I draw this bar like this. Okay, and the point C is here. Okay, and it's 500 Newton. Point down, and the distance here is 2, distance here is 3, and he wants you to solve the reaction force or the force acting at the terminal. Okay, so the textbook, he assumed FB is a tensile and FB is a compression. But actually, I'm not that smart. So if I don't know the direction of the force, I will assume everything is tension. Okay, the textbook assume the force at A is a tensile, tension force, tension, and the force at B is compression. But I would like to assume the force at A is tension. Okay, and the force at B is also tension. I like to assume everything is tension in such problem, and then I call this. Let's say how to can I call this? Okay, I call this RA. Okay, I call this RA, and it's called RB. Okay, and then we do the rigid body equilibrium. Okay, because everything is static in this course. So, and right now we don't have to consider any moment of the system because there is no external moment. So we don't have to consider moment balance. The moment balance is 0 equal to 0, so that's useless. We only have to consider the force balance. So the force balance, okay, up we have the RA point up and C as a force here point down to minus 500. And here RB minus RB is equal to 0. So we will have RA minus RB is equal to 500. Okay, let's just tell you, okay, we use rigid body equilibrium. We get the equation. But when we look back to the problem description, it looks like we only have this equation to use. And we have one equation of course, we cannot use this equation to solve these two unknowns. So we have to find another equation to solve the problem. Okay, so that's called statically indeterminate. So it said when the equilibrium equation is not sufficient to determine both reaction on the bar, it's called statically indeterminate. Okay, and then you have to find a compatibility equation. Also, to me, it's called find a constraint. Okay, and then constraint, okay, it's 99% is from deformation. Okay, from deformation. Okay, so we have to use the deformation to find the deformation constraint of this system. And actually, I have done a video to demonstrate a real statically indeterminate problem for axial loading member. Okay, so please look at the video. Okay, if you look at the video, you will understand why the constraint equation is okay. Well, you can understand why. Okay, and that's the reason for the constraint equation. Okay. So the constraint equation is like this. Okay, so I apply an external loading here. Okay, and here you have a deformation here, deformation of AC. And also this external loading, it also had created a deformation at AC section and the deformation at CB section. Okay, and overall deformation is equal to 0. Okay, can you imagine that? Okay, so if you don't know, just look at the video. I just look at the video. I use the real stuff to demonstrate this. Yeah, because this bar is constrained in constraining AB. Okay, so here the AC is the extension and CB is the contraction. Okay, and the extension for the AC must be equal to the contraction of CB because this bar is confined in this space. So the extension here, the amount of extension here must be equal to the amount of the compression here. So that's why the deformation add together must be 0. Okay, and this is the compatibility equation, also called constraint of this problem. Okay, so and don't forget how to calculate the deformation of the axial loading. Okay, the deformation for the axial loading is normal force times the L divided by A and E elastic modulus times the area. Okay, so we have the normal force on AC section and times the AC length divided by EAC and times the AAC. Okay, plus the NBC times LBC divided by EBC times ABC and equal to 0. And in this problem, because this bar is made of same material, so EAC is equal to EBC. Okay, we call this E, and also it's the same bar and no change on area. Okay, so AAC is equal to ABC, so that we'll call it this A. So this will have this equation like this: NAC times LAC and EA plus NBC times LBC divided by EA equal to 0, and then we multiply EA. Okay, so we'll finally reach this conclusion: NAC times LAC plus NBC times LBC is equal to 0. Okay, and LAC, we know LAC is 2, and okay, and LBC is 3. Okay. And next thing is, okay, what is the NAC and NBC? What is this? And what's the connection between the NAC, NBC with the reaction force at A and reaction force at B? What's the connection between the NAC, NBC and the reaction force at terminal A and terminal B? So how to resolve this issue? Yeah, don't forget we use the cut section method. Yeah, once again we also have to use the cut section method. Yeah, I keep saying that. Cut section method is you need to use this all through the whole semester. The cut section method is very annoying. Okay, so cut section method, because we want to know the normal force at AC section and BC section, so we need to cut here. we need to cut here. Okay, so let's draw the section balance here. This is here, and this is A. Yeah, and the other is here. This is A, and this is okay. So this is C, and this 500 Newton. Okay, here AC. Oh, yeah, that's B. Okay, and then put our RA back in RA. RB RA, and here we yeah, here in the cross section, in the cut section, I don't know the direction of force, right? So I just assume everything is tension again. Okay, so this is for NAC, right? And this is NBC. So if you use cut section method, okay, then you can find a relation between NAC, NBC, and RA and RA. Okay, how? Okay, let's start with this. Okay, we start from this first. So we will have the RA. Okay, it's point down. So minus NAC is equal to 0. So let's tell you NAC is equal to RA. Okay, that's first one. Okay, then here the second one here. Okay, RA point up and 500 Newton point down. Okay, minus 500 is equal to it's minus NBC point down. Okay, NBC point down, so equal to 0. So what this tell you? It tell you NBC is equal to RA minus 500. Okay, so you get this two, NAC actually equal to RA and NBC actually equal to RA minus 500. And use these two back to in this equation. So what we will have? You will have RA. Okay, so you need to combine these two together. Okay, see the magic. See the magic. Okay, see the magic. Okay, see the magic. Okay, see the magic. Okay, it's really a magic. Okay, see the magic. Like 小钟 magic. Okay. So what do we have? Okay, you will have RA times 2, right? RA, NAC equal to RA times 2. And NBC is equal RA minus 500. So plus RA minus 500 and times 3 equal to 0. So what is tell you? It equals, it just tell 2RA plus 3RA minus 1500 equal to 0, right? So so what's this tell you? So it will have the 5RA equal to 1500. So RA equal to 300. See, we solved the RA. Magic. Okay, so RA is 300. So 300 minus 300 minus RB is equal to 500. So what's our RB? RB is minus 200. Okay, so that means okay, the meaning of this solution is RA. Yeah, RA is really a tension and it's 300 Newton point up. It's really a tension, 300 Newton point up. Okay, and RB is because it's negative, so actually its direction is compression, and it's 200 Newton. Okay, that's the same as the same answer. That's the same answer as the in textbook. Let me check. Okay. Yeah, RA is 300 and RB is 200 and compression. RB is compression. So, so let's once again I tell you that I want to address that. If you don't know the direction of the force, you just assume everything is tension, especially axial loading problem. This won't hurt your answer. Okay, that won't hurt your hands. You will get the same result. Okay, so that's the typical statically indeterminate problem. And for the next few PowerPoint and next I will have some statically indeterminate problem in axial loading member for the next 2 or 3 slides, and I have made some video for that. So just watch the video and practice by yourself. I think, and because most and this problem are very similar to each other, so I don't think I really need to explain it one by one in class. Okay, they are very similar to each other. Okay, yeah, looks like the competitivity equation is difficult to find, but when you do some practice, you will see actually there's some trend or some hint. Okay, not that difficult to find a competitivity equation. Okay, so I just start the video here. Okay, see you in another video. Bye bye. Okay.